Welcome back, everybody, and welcome to our online students. Today, what we're going to do is take a look at left-handed and right-handed molecules, and we're going to take a look at something called sigma bonds and pi bonds, being able to identify those and count those. Now, the first thing we're going to take a look at is something called aromatic and polyaromatic compounds. This is just kind of an odd and end sort of thing that I'm wondering if the authors of the textbook weren't sure where to put this. And so this is where they snuck it in. And so what makes something aromatic is this structure here. We have 6 carbons forming a ring, where we have each of these corners would be a carbon. And chemists are often lazy and don't like to write all of the carbons and hydrogens and such, so they might go something like this. And then there's double bonds in there. And so there would be alternating double bonds like this. And then those double bonds, they resonate. This is a resonant structure. So the double bonds are not in these 3 spots, they actually move around. And because of that, when chemists get even lazier and they draw this molecule, they might draw it like this. And so what this is trying to say is that there's 6 carbons, 1, 2, 3, 4, 5, 6 carbons, there's 3 double bonds, and they are moving around like that. Now this is called an aromatic ring, And the reason it's called that is because it smells. It has an aroma to it. So compounds that have this structure oftentimes have an aroma that you can smell. So it's called an aromatic ring. Now polycyclic aromatic rings, poly means many, cyclic means circle, and then aromatic ring. So it's just several of these joined together. And we see this oftentimes in nature. So there's a lot of compounds in nature that use this structure. So it's a resonance structure, polycyclic aromatic hydrocarbons. Okay, that's just kind of an odd end. Moving on. Now, left-handed and right-handed molecules. Molecules can be left-handed and right-handed. I mentioned this a couple episodes ago. I want to say a couple days ago, but for people that are just kind of clicking through the videos, it's going to be next, 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 next. Or is it Netflix next? Netflix? I'm not sure how people do that. But okay, so left-handed and right-handed molecules. What's the deal with that? So what I did is I made 2 molecules here. And this one here, it's got a steric number of 4. There's 4 things coming off of it. It's tetrahedral, and I'm just going to call this a molecule here. And this molecule is a mirror image of this molecule. Like if I were to put a mirror right here, they'd say, hey, how are you? Oh, I'm your mirror image. I'm your evil twin. Heck, Jekyll, Hyde. Okay, mirror images of each other. And you might think, well, they're the same. There's white and blue and green and orange and black. Yes, they both have them. They are the same. And if you were to take one of these things and stick it on your tongue. So for example, if you had one of these things here, one of those, do you have one of those? I don't believe you. Okay, thank you. All right, we're just confirming. Now, we take one of these things, and this molecule comes floating around, and it lands on your tongue. And so what I'm going to do here is I'm going to say, all right, it lands on the tongue, and we've got some receptor sites. Receptor site where it lands on the tongue here like this. And I'm going to say here, this one's green. And this one here is orange. And over here I've got blue. And we're just going to say these are 3 receptor sites here, or it's a receptor site where the molecule touches and the tongue recognizes that and it says, that's tasty. Maybe that's caraway, for example. And so we take the mirror image of that, say here's my mirror image now, and I'm going to take my mirror image and I'm going to put that on our receptor site. And so I'm going to line this up here, so I'm going to get my green here, my orange, and so I'm going to start, here's my green, and then I get my orange one here, and then it doesn't work. It doesn't match up, and you're saying, oh, well, just flip it around like this, right? Well, there, now I've got my blue there and got my orange there, but doesn't work. So one of these molecules is different from the other. They're mirror images, but they're not the same. And they biologically act differently. So for example here, we've got caraway and we've got spearmint. And they look very similar. They're mirror images of each other, but when they hit your tongue recognizes them differently. And this is because they have what we call in there a stereocenter. That's a carbon atom here, carbon atom, that has 4 unique things attached to it. So as we take a look at these structures here, you can see that the carbon is circled, and it's circled over here. And this carbon has 4 unique things attached to it. It's got a hydrogen, it's got a carbon and a carbon-oxygen over here, carbon-carbon over there. This side is different than this side. And then down here, we have something different as well. So there are 4 unique things attached to that carbon, 4 unique things, and that makes it a stereocenter. So you have to have 4 unique things attached to a carbon. And this is what we end up creating then, is something called a stereoisomer. Stereo means like left and right. If you have headphones that are in stereo, you have left and right. We have left and right-handed molecules. Left and right-handed molecules. And sometimes we'll label it as plus, sometimes minus. Sometimes we go R and L for right and left. Right and left. There's a part there about enantiomer. Don't worry about that. You'll see that when you get into organic chemistry, if you stick around for that. Now, where does this come from? This is one of those wonderful, wonderful stories. There was this guy named Louis Pasteur. You may have heard of him, especially if you're a biology student. So Louis Pasteur was sitting at his estate and he's drinking wine, and he noticed that in his wine cask he had these crystals forming at the bottom. And it's kind of hard to see, but here's a cork, and right here we've got these crystals. And these crystals are bifurcated. That is to say that they come up like this, like the letter V. And the crystals, they look the same except that they're mirror images of each other. And Louis Pasteur was looking at that and he thought, well, that's kind of weird. I wonder what the deal is with that. And so he took a tweezers and he separated out these crystals. And he made a pile of one type and a pile of the other, and then he tried testing them as best as he could. Melting point, solubility, stuff like that, color. And they seemed identical. They seemed identical. Now what he didn't know is that these are tartic acid molecules, would make these crystals, and they are mirror images of each other. They have a stereocenter. That is to say, they have a carbon atom here with 4 unique things attached to it. It has a stereocenter. Now what he did is he took these crystals, he dissolved them in water, and then he shined polarized light at them. And so polarized light, if you ever have like polarized sunglasses, what they do is they filter out the light where the wavelengths are going in different directions. So it tries to line them up, only lets light through that's lined up, so polarized like this. And what he found is when he put the crystals in a sample here and he let the polarized light go through, that it would rotate the light to the left or to the right. And this is why we call these left-handed and right-handed molecules. Which direction do they rotate the light? Now, curiously, if you take the two and you mix them together, then it doesn't rotate light anymore. The light goes straight through. It's like, whoa, that's weird. Now, he had no idea why this happened. He would just call, well, this is left-handed, this is right-handed. I'm not sure why this is happening, but this is what it is. And so we would say then that these molecules have a chiral center or a stereocenter. That is that we have 4 unique things attached to a carbon. 4 unique things attached to a carbon. So I'm just picturing like a test type question. If I gave you a molecule and I asked you, can you circle the chiral center or the stereocenter? Can you find a carbon atom that has 4 unique things attached to it? Can you find a carbon atom with 4 unique things attached to it? So this would be a test type question. Looks like this here. Here's 4 molecules. can we find carbon atoms on each one that have 4 unique things attached? So molecule A, can you identify a carbon atom on molecule A that has 4 unique things attached? Okay. We're not seeing it. And that's okay. That's all right. So let me do this. I need a long, pointy stick thing. Okay, yep, now go up 1, right there. Yeah, okay. Now that carbon atom has a hydrogen attached to it. It's got the CH3, then it's got a 2-carbon string on this side and a 3-carbon string on that side. Okay? Well, this is why we practice. So there's 4 unique things attached to it. So this molecule could have a left-handed and right-handed version, and you identified the chiral center or the stereocenter. Okay? So would you please pass that to somebody? This is very appropriate. You're wearing a hat today. Okay. So the next molecule, molecule B, can you find a carbon atom that has 4 unique things attached to it? Yeah, and you'd be correct. Nicely done. So keep the light on there for just a second there, please. Yep, so everybody can see that there. Yep, so that carbon atom has 4 unique things attached to it. Even though it's part of a ring, the ring is not the same on both sides. Okay, nicely done. And then let's pass that on there. And so the last molecule there, molecule C, can you find the carbon? Oh, you are fast. Oh, keep it there, keep it there. Yep, that carbon atom has 4 unique things attached to it. Nicely done, thank you, thank you. Now, the funny thing, I shouldn't say funny thing, the neat thing about Louis Pasteur, have you heard of another story of Louis Pasteur? What is he famous for? Pasteurization, right? Before that, nobody could drink milk. Well, I mean, you could, you just die. But yeah, he's famous for pasteurization. He's also famous for a vaccine. Do you know what vaccine that is? Oh. Anybody know? I mean, he did a lot of stuff. A lot of cool stuff. All right, so, okay, true story for you. Louis Pasteur is at his chateau, drinking red wine, looking at crystals, and there's a knock at the door. And he goes and he opens up the door. This guy's here, and he says, "Hey, Louis," except he says it in French. "Oi, Louis." The guy's knocking at the door, and he's in a panic because his son was bit by a rabid animal and has rabies. And this is very sad because at this time, there is no treatment for rabies. Let me rephrase that. There was a treatment for rabies. You put a gun to the person's head and you shoot them. And the reason is because rabies is an absolutely horrible way to die. It is so miserable that it was considered merciful to just kill the person. Now this father's got his son who's been bitten by a rabid animal, and he's like, "Louis, you're like the smartest person in the village. You figured out how to pasteurize milk. Please help my son." And so Louis says, "All right, I will help you, but here's the deal. You can't tell anybody because in France, practicing medicine without a license will get you in jail, or maybe even the guillotine. So you can't tell anybody. But I've been doing this experiment with rabbits, and I think I've got something here that might help your son." And so what he does is he takes what we call an attenuated virus. He takes the rabies virus from the rabbits, and he inoculates the kid. He vaccinates the kid. And the kid ends up getting cured of rabies. He doesn't develop rabies, and he doesn't die from this. So this is like one of the first demonstrations of vaccination. Now, this father was very, very thankful. It's like, "Louis, thank you so much. I will do whatever I can for you. What would you like me to do?" And Louis says, "Oh, don't worry about it." Except he said it in a French accent. "Oh, it's all right. So don't worry about it. And just don't tell anybody, because I do not have a license. I can't do a French accent. It's terrible. And I apologize to anybody who identifies as French. So he tells the father, don't tell anybody. So what does the father do? He tells everybody. Louis Pasteur saved my son. This kid would be dead if it wasn't for Louis Pasteur. All hail Louis Pasteur. Isn't this wonderful? This is great. Now fast forward a few years. Louis Pasteur dies. The French, they don't kill him, by the way. They create the Pasteur Institute in France. And France gets into this little spitting match with Germany. They called it a world war. And the Germans get to the Pasteur Institute. And when they're at the Pasteur Institute, they find Louis Pasteur's crypt, his tomb. And they are ripping up the Pasteur Institute, burning things because it's a war and Louis Pasteur is on the wrong side, according to the Germans. They get to the crypt and they're going to desecrate Louis Pasteur's gravesite. And a little old man comes out, true story, with a mop in a heavy French accent and tells the Germans, no. Stop. This is the tomb of the Louis Pasteur. You shall not desecrate this grave. That old man was the boy that Louis Pasteur saved from rabies. I'm not crying, you're crying. Okay, I'm sorry it gets really sad because unfortunately the guy, I think he commits suicide shortly after that. Yeah, I'm sorry. Should I have just stopped before that part? Yeah, I'm sorry. Okay. Now, left-handed and right-handed molecules. We started this unit and I told you about this drug called Nexium. And Nexium has left-handed and right-handed molecules. So does albuterol. Albuterol is a drug that is used for people that have asthma, and it is a bronchial dilator. It causes the muscles in your bronchioles to relax. However, it is left-handed and right-handed molecules. One of these molecules, this one right here, one of these molecules causes the bronchioles to dilate. The other one is like amphetamines, but they're mixed together in albuterol, the inhaler. And I ran into this because my child ended up having asthma and we had to nebulize him. We had to give him albuterol before he went to bed. And so that his bronchioles would open up and then he would wake up in the morning. So as a parent, this was important to me, because I like my kids. So I give him the drug, but it's mixed with left-handed and right-handed versions of albuterol. And this one here would make the kid crawl up the walls like he's on amphetamine. So you get him doped up on this stuff and say, okay, go to bed. And the kid's like, woo, right? He's just all jacked up on this stuff. So as a parent, I'm looking for a solution to this. I want my kid to live, but I also want to sleep. So I go to the pharmacist and I say, is there any solution? And the pharmacist says, yes, somebody figured out how to separate the left-handed and the right-handed enantiomers here, the left-handed, right-handed molecules of albuterol. And now they've separated them, and you just have the one that is the bronchial dilator, not the one that has like the amphetamine effect there. And I was like, okay, sign me up. And the pharmacist says, yeah, but it's going to cost you. It's not generic. It's going to be expensive. Now, I'm sleep deprived at this point. So I'm like, shut up and take my money. This drug is called Xopenex. And for those of you that are asthmatic, you may have heard of albuterol, you may have heard of Xopenex. Xopenex is just one of these two molecules, just one of the mirror images of these two molecules. Okay, so enough with stereomolecules. Now, the last thing we're going to look at is something called sigma bonds and pi bonds. Sigma bonds, sigma bonds, these are single bonds. So for example, if I have a carbon-carbon single bond, that is a sigma bond. Now a pi bond is where we have a double or a triple bond. And so if I have a double bond like this, or if I have a triple bond like this, here's where it gets a little weird. And that is, I'm just going to go like this. I'm going to say sigma right here. So that's a sigma bond. Now when I have a double bond like this, one of these is a pi bond, and it doesn't matter which one. I'm going to say pi. The other one is sigma. Like this. And then when we get to a triple bond, we're going to have a pi bond. We're going to have a pi bond. And we're going to have a sigma bond. And you might ask, who cares? Right? We're just sharing electrons here. What's the difference between this one and this one and this one? Well, it has to do with where the electrons are in the bonds. Sigma bonds are going to be on like the direct line, the shortest distance between these two. This is where the sigma bond would be. The pi bonds are actually above and below. These are going to be overlapping p orbitals, which, okay, it's gobbledygook, but the point is the pi bonds are actually like up in this region of space here and here, okay? Not that I would test you on that. What I want you to be able to do is, can you look at a molecule and count up the sigma and pi bonds? Can you identify where the sigma and pi bonds are? So for example here's a molecule, and this is a chemist being kind of lazy. And so on this molecule, we've got carbon, double bond oxygen like this, and then we've got OH like that, and then we've got CH, and then we've got CH3, and then we've got NH2. Now, it tells us here, it says total count is 12 sigma bonds and 1 pi bond. And so if we try to identify these here, let's see if we can't find these here. I'm going to try to find my sigma bonds. Okay, so sigma, I'm going to go, maybe I'll go like this. I'm going to go sigma. One of these is sigma, and one of these is pi. And then here's a sigma, here's a sigma, sigma. Okay, so I've got 1, 2, 3, 4, 5 sigma bonds and 1 pi bond. But it tells us up there, tells us we've got 12 sigma and 1 pi. Where are those other sigma bonds? It's like they're hiding. Can you find them? Yeah, what are you seeing? So the carbon atom and the H3. Yep, there's bonds hidden in there, but I was too lazy to draw them. But you saw through that. Okay, so I'm just going to go like this because chemists are sometimes lazy, but I'm not lazy for you because I love you. Okay, so here's a sigma. Oh, yeah. Oh, isn't that sweet? This is the last day that we're recording. Tomorrow I'm going to hate you. This is when the Dr. Hyde version comes out. Okay, so sigma bond, sigma, sigma. So now we've got 1, 2, 3, 4, 5, 6, 7, 8. We're 4 short. You were correct. We need a couple more. Where are they? Where are they? Murmur, murmur. Help me. Between the, here? Yep. Okay, so there's some hiding in here. We're going to have a couple here like this. Okay, so here's some sigma bonds and sigma bonds, okay? And so that gets us to 8, 9, 10. I think we're missing 2 more. Missing 2 more sigma bonds. One on the OH here. Yep. Like that. Like, okay. And then on the CH. Excellent. So the CH would be like this. Oh, wait. Hydrogen. Okay. So there's our 12 sigma bonds. Now, for the bonus prize, can you see a chiral center, a stereocenter? Is there a chiral carbon on this molecule? Yep, there is. Where is it? In the middle. Down, getting warmer, red hot. Yep, right here. There are 4 unique things attached to this carbon atom. So this would be our chiral center. And we might even go like that. Yep.